Our first speaker is going to be Lee Howard. And we're very, very lucky to have Lee. He has done so many things. He was co-chair of V6 Ops at the IETF for quite a few years. He's been on the AARON board. He's done a very large Ipv6 deployment. And then, of course, that unforgettable draft of his to deprecate IPv4, it will live in infamy. So, and I'm going to let Lee tell you about how he got started in the IETF. I know quite a few of you are interested in how to make that jump if you've not done it. So, Lee, thank you so much.
Thank you. Yes, let me make sure I've got my volume check right. So, yeah, my draft to deprecate IPv4, or to declare it historic, let's just say it did not find consensus. So I'll start off with, almost 20 years ago, I was at UUNet, largest ISP in the world in terms of connecting commercial customers, commercial offices. And in addition to my other responsibilities, I took over the IP management system. And I had a very small team who was in charge of making sure that we had justifications for our IPv4 assignments. And in that role, I started becoming active at AARON, the Regional Internet Registry. And I kept getting to the mic and making comments on a mailing list. And it turns out, my impression is that when you speak up and say things that aren't dumb, people think you're smart. You don't actually have to say anything terribly smart. You just have to say a lot of things that aren't stupid, and you look smart. So I've taken this practice into Nanog and into other places. I was actually on my way to a meeting in Dar es Salaam, Africa, with somebody who later hired me at Time Warner Cable, and we just got to know each other very well. And I kept saying things that he thought were not terribly stupid. And this is also, I've found every time I go into a job interview and they ask me a question about some technology, and I say, I don't know. I mean, I know it stands for this, and I know it has something to do with this. If I do 30 seconds of literally everything I know on a topic, people think I know something about the topic. It's really strange. I got to, so this guy then hired me. So I did several years at a very large ISP. I went to an enterprise network in the US. And then he said, hey, come work for Time Warner Cable, which was the second largest cable company in the US, and I guess the third largest ISP at the time. Come work for us and look at technologies that are 2 to 5 years into the future. So not quite the futurism that Nalini was talking about with the 10-year horizon, but a little bit more, get it to the point where we can actually start looking at products that we're going to see into our network. And fairly quickly, and so he said, this is what I need you to work on. Go figure out where technologies are being developed and where you need to be in order to be part of the conversation. So I pretty much instantly, during the interview, I said, well, it sounds like IETF is going to be a key thing. And he said, absolutely, you have to go to IETF. So that made that one easy. The next part from that was, well, okay, where in the IETF? Great, I need to go to the IETF. Fantastic. I pull up the list of working groups and I go, there's 150 working groups. I can't subscribe to 150 mailing lists. That's just, I don't scale that well. So I did some analysis and I went to a meeting or two and sort of dropped into working groups that had interesting titles. And I did find that if I walked into a working group that had been active for a couple of years, I had no idea what was going on because there was so much context for, people already understood the problem very, very well. They'd been talking about it for 2 years. They understood their general solution space pretty well, and they were arguing about the small defined details. Well, if I don't understand MPLS, then arguing about where, what data goes into LDP, where in a packet, is not something that I'm going to be able to keep up with. That's not a conversation that I can have. But if I get involved with a working group early in its existence, then I can have a lot to say about how the problem is defined and what the solution space can look like. And I, as a network operator, had a different perspective than a lot of people at the IETF, which is largely, in my perspective, largely dominated by vendors, equipment vendors, and academics. And that's appropriate. I mean, people who are going to be, people who have done research saying, here's how things could happen, academics, have really important things to say, and equipment vendors who have to implement whatever specs we come up with have to be there. But then operators are the ones who have to deploy this stuff and make it work with the existing set of network protocols. And that's where it sort of got to be, I felt like I, as a network operator, had more to say, and often, I guess Laney would probably agree, various kinds of network operators, because it's a different perspective than a lot of people at IETF are used to, we don't speak in a way that they understand, or that they're most able to hear, or they're just not ready to hear what we have to say. So there's some definite challenge there in terms of cultural context, but I think that's a very useful friction to have. One of the things that I came up with very early, after 3 or 6 months there, I said, you said to look at things that are 2 to 5 years from things that we need to have in our network. And that's about exactly the time frame that IPv6 is going to be critical to us. And so I need to know, how, let me know, I'm getting more and more nervous about IPv4 runout and our need for IPv6 and how long it's going to take us. Let me know when my anxiety is going to be, as it keeps getting higher, let me know when I should come and pitch to you a proposal about what we should do about it. And he said, you should go manage our v6 deployment strategy. Just go make it happen. And I went, oh, okay, just go make it happen. No big deal in a company of 50,000 people and 15 million users. How hard could it be, right? So yeah, 8 years later, I don't realize that's an exaggeration. It took us really not long at all to get IPv6 deployed in the backbone. That's pretty simple routing, and then v6 to the to our data centers, so we could do our provisioning and management systems. v6 down to the edge. Eventually, v6 CPE was an ongoing struggle. Getting a CMTS, that's the cable edge device, to support v6 well. Those were ongoing struggles that we had. It took us a few years. We found lots of bugs. We got them fixed. So hopefully anybody doing it now will have many fewer bugs. I have long said that I can talk for hours about IPv6, and today we're going to see if that's true. I've got, because this set of topics is so big, I've got a big chunk in the morning. However, if I stand here and just lecture for an hour and a half, it's going to be dull as dirt. So please, as I'm talking, get up, ask questions. It's a little more challenging for me, but that's great because it makes it a much more interesting presentation, and I've decided I have an incentive. Anybody who asks a question at the mic can get a sticker. It's a cutout sticker of a cheetah, and the dots on the cheetah say IPv6. And I did, as you may have seen, the old stickers that were horse and buggy, and says this, this device only runs the old version of the IP protocol, internet protocol. I decided I was tired of giving stickers to people who don't have IPv6. People who have IPv6 should get stickers, and these are cool stickers because they're cheetahs and IPv6 is fast. How many people in the room have actually done something with IPv6? Fantastic. That is that's more than half. It's almost everyone, and that's great because I was going to really give you a hard time when more than half of India has IPv6 already in terms of number of users. Or when you go to a website that has IPv6, more than half the country is using it. Did you learn about IPv6 in school? Are they teaching IPv6 in school? I'm seeing some nods and I'm seeing some head shakes, and that's crazy. Why were we teaching IPv4 when more than half of the internet is IPv6? That's ridiculous. I will point out, though, that of the top 50 websites in India, only 9 have an IPv6 Quad A record. Only 9 are IPv6 enabled. What's really interesting about that is I also looked at which ones could be, and another 21 websites of the top 50 websites in India are hosted by either Akamai or Cloudflare, which means all I have to do is press the Give Me IPv6 button, and the number of websites would triple. So good luck with that. What else did I want to say? So IPv6 security in the cloud. So this is sort of I'm going to be talking a little bit about IPv6. I'm not going to go into too much detail on the protocol mechanics, since a lot of people here have some experience with it. But I'm going to talk about specifically security issues, and that's sort of the IPv6 focused part. I'm going to come back and talk about how cloud computing helps mitigate a lot of the security issues and other reasons that it could be useful. How many people actually have a website or some other service in the cloud? Okay, a few, good. In this case, I'm generally going to be talking about major cloud providers. I'm not talking about building your own cloud, because building your own cloud, I can't tell the difference between building your own cloud and building an automated data center. I don't understand what the difference is. Using a cloud provider, that's sort of, it's a black box. So let's figure out which button to press. Is it that button? Is it? Oh, make sure it's on. That's a good idea. There we go. So my favorite thing to start with is a lot of people say, we don't need IPv6 because we have NAT. NAT is good. NAT saves us because we can do address sharing. Here's this beautiful thing where you've got IPv6. You've got two hosts going to a firewall, a web service, something, and you just log their address. And you've got an address logged saying, this top host came to me and this bottom host came to me at similar timestamps. What could be easier? That's the way it ought to be. Well, unfortunately, as you probably know, in IPv4, when you have NAT, you can have two hosts going to someplace and they're logged with exactly the same address. Sure, you could log source port. Yes, you could log the timestamp. You would need to log both of those things if you wanted to go back to whoever was hosting those devices and figure out who was actually using those devices at that time. If you're trying to do forensics, if you're trying to do an investigation into an attack, if you're trying to report a crime, you have to provide that much data and then hope that whoever the ISP was or the mobile carrier was logged that information and can provide it to you, and hope that if you provide that information to law enforcement, they have any idea what you're talking about. All of those things, that's a whole chain of potential problems that bothers me. People like to talk about, things are just going to be so much better in IPv6 because it's so much more secure, or IPv6 is so hard because it's so much less secure. I keep hearing these things, and I don't really like structuring talks around myths, but there are a couple that just keep coming up. One is, we don't have to worry about IPv6 because we haven't turned it on in our network yet. Yeah, great. I'll talk about that some more. NAT keeps us secure. I'll tell you how that doesn't work. Yeah, people think that host scanning is hard in IPv6 because you've got trillions of addresses. I'll show you how it's not so hard. And we have IPsec. IPsec makes us more secure, right? Well, that's probably easy to dispense with. In no particular order. We haven't turned on IPv6, therefore we don't have a security issue with IPv6. Unfortunately, actually I'm going to say fortunately, IPv6 is on by default. Practically, every device in your pocket, on your lap, on your desk already has IPv6 enabled. And that's true whether it's your home computer, a work computer, certainly every mobile operating system, it's already on, which means that at least link local works because it's automatically enabled, which means if you're on a local network, you can use IPv6 to communicate with other devices on that network. And unless they have host protection that looks for IPv6, if one host gets compromised, you've got an easy pivot point to the rest of the network. That's pretty simple and straightforward. But it even gets worse because I've actually seen this in the wild. Firewalls that said, I can only inspect traffic where I understand what the protocol is, and since I don't recognize IPv6, I'm just going to let it go on through. Somebody else is going to have to inspect that traffic for me. That's a crazy security policy for me, but apparently that's what happens when you can't recognize a protocol. I've even heard of that. I haven't seen this, but I've heard of it with intrusion detection and intrusion prevention systems. So if you think that you're secure because you haven't enabled IPv6 in your network, it could well be that your firewall and your IDS aren't even examining inbound IPv6 traffic. So much for your security, right? And even if your firewall could inspect it, if you're using a transition technology that's a tunnel, that tunnel is probably just going straight through the firewall because the firewall says, oh, it's a protocol 41. I just forward those because I've got a tunnel terminator someplace else in the network. And the last one is, that IPv6 is on at home. So if you tether to your phone and your mobile carrier has IPv6, or you're at home and you've got some kind of fixed landline internet service at home that's providing dual stack, it's already on. You turn on your VPN, and now what happens? I'm going to talk about that in a little bit more. But first, NAT as a firewall. People say, well, because I've got stateful NAT, I need stateful NAT to protect my network. And I hear this over and over and over, and it drives me crazy because, well, let me show you what the state looks like. So you send a packet out. So I've got a source address of this device down here. And I've called this source address 192.168.1.4 and a source port. And its destination is this server up here on the left, 192.0.2.80. And so it sends that out. Now, of course, you're probably used to some device at the edge of the network is doing network address translation. And it's going to map and say, OK, anything coming from this source and going to this destination is going to have we're going to map and say these packets get forwarded this way, rewrite the headers, and then so that any traffic that comes back we know that we forward it back to this machine on the network rather than some other machine inside the network. That's what we expect to happen. That's 5-tuple mapping, because you're mapping the source address and port, the destination address and port, and the protocol number. However, what if you're doing peer-to-peer networking of some kind? What if you're doing gaming? Even if you're doing SIP phone calls? What happens is you connect to this server, and that server then says to somebody else who's trying to reach you, hey, contact this user at this address and port. Okay, well, if you contact this user at this address and port, then machine B sends a packet over to whatever address it was given, 192.0.2.133, port 4675. If the NAT box has done 5-tuple mapping, that packet's going to get dropped because it's not coming from a source port that it recognizes. So what actually happens almost, I'm not going to say almost all the time, most of the time, what actually happens is you get a 3-tuple mapping, which says, once I have an outbound packet, established state that says anything inbound to this address and port, anything inbound from anywhere, just forward it to that machine. What's crazy about that is, this is to some people, okay, well, so you just have a firewall. That's not a firewall. That's not even an ACL. That's allow any inbound. And it could be any protocol, any packet, anything. Yes, you specified which port it's going to be forwarded to, but there's so many buffer overruns and cross-site scripting attacks. So many different things could happen inside these kinds of packets that that is no security at all. Once you have any kind of connection outbound, anything is allowed inbound. Now, what really bothers me about that is in modern internet applications, if your computer's on, there's usually some kind of outbound communication. Your computer is doing constant keep alives and connections out, even just health checks out to the internet. So there's almost always a path inbound to you. So what happened to your security? So that's why I always push back hard on the theory that NAT provides security, and therefore we need NAT in IPv6 because it provides the security that we had in IPv4. No, what you need is a stateful firewall that actually tracks SYNs and only allows response packets. And for specific protocols, you can do application protocols and do additional mapping if you need to. Stop for a minute. I've been rambling for a few minutes, and I want to make sure, I want to re-encourage, but we've got stickers. Anybody wants to come and ask anything at any time? So let's talk about host scanning. People keep saying, well, we've got, I did the math, but I can't even count it. 100,000 million, billion, trillion, quadrillion, quintillion, 18 quintillion addresses, or whatever billion addresses, trillion, I forget what it is. That's a lot of addresses to scan. Obviously, you can't just start a ping, a for loop pinging every possible address in all that address space. But you don't have to. With a little bit of cleverness, you can realize that with any given /64, human behavior, there's likely to be something that's at : 1 or : 2 or : 80, or using some words. Since we have hexadecimal, we can do clever things with cafe, beef, dead, dude, whatever. And then the other thing is, frequently people will map IPv4 addresses into those last 64 bits. And if you can scan the IPv4 internet, you can scan possible addresses at the bottom of a /64. But that's not all. There's even more clever things you can do. Oh, and I've tried to do in a couple places, list the relevant RFCs that provide more detailed information. The slides will be online, and you'll be able to dig these up later. I haven't kept in mind which ones I co-authored or which ones came through a working group that I was chairing at the time, so I can't claim credit for a lot of things. It gets even more clever. So since since stateless address auto configuration, by default, the original design was that you would take your MAC address from your network card and make that the last 64 bits. You take you've got you've got your, I forgot how many bits it is, the 24 bits? Thank you. Thank you very much. So 48 bits of a MAC address, stick the letters FE in the middle, and there's your MAC address. Well, that's great. That's still a lot of digits to have to scan through, except that there's probably half a dozen, 10, 15 OUIs assigned to the most popular network cards. So if you know who the most popular network card manufacturers are, or even just which chips they are, then all you have to do is scan the last set of bits. That's pretty trivial. That's not a huge set. One of the other clever ones that I read about in the documents from the previous slide, you can do a DNS lookup. Either just say, give me, just do a zone transfer for everything within a reverse zone, or go through and digit by digit for each /64, do a DNS lookup for PTRs. And if you get a no data, that means, oh, there is an authoritative zone for this /64. Not that particular record necessarily. Now I just have to scan that /64. But I can skip every 64 where I get NX domain, because that means there is no PTR within that NX domain. Pretty useful there. And then of course, hey, if you have access to a server someplace that lists incoming connections or that lists potential systems that you could connect to, that's a list of host bits. So you can just go say, well, I know that if I'm going to do, if I want to torrent some large file, and here's a list of v6 hosts that have it, problem solved. I've got a list of hosts. So, okay, so much for that misconception. There are some mitigations, and I of course, want to discuss mitigations wherever I can, because it's a security talk. So first thing is you can just block ICMPv6. I don't recommend blocking ICMPv6. You can block specific messages, but fundamental, actually you probably already know this, because most of you have done something with IPv6. You really need to have path MTU discovery working, which means you need to allow the packet to big message to come in. So you can't just block all ICMPv6. But you can block other messages as you choose, or you can rate limit them, similar to the way you would probably in IPv4. And of course, we've got privacy extensions. So even if somebody does discover your host, you can, your address in many cases changes every 24 hours. Or you can reset that and have it change every hour if you want to. That only helps if they discover your privacy address and not your Slack-derived, your Mac-derived EUI64 address. But there's still some mitigation there. Yeah, this used to be, I don't hear this as much anymore. I used to hear this, 8, 10 years ago. I heard a lot, well, IPv6 is going to be much more secure because it has IPsec. Well, that would be great if IPsec actually worked everywhere. If every implementation of IPv6 actually did include IPsec. All of the IoT stuff we had yesterday, I'm pretty sure most of those implementations were not compliant and didn't include IPsec specifically. Some crypto, depending on which device we're talking about, but probably not the full stack. And yeah, what was the other thing about? Oh, and of course, IPv6 is no more secure because of IPsec than IPv4 is. We have IPsec in IPv4. It was backported. So where's the advantage there? So okay, that's sort of the things that most people talk about when the first things they think of when they think about security with regard to IPv6. There are some specific details security-wise that people, that I think that not everybody knows about, that I want to make sure I get into in order to have a thorough discussion of the risks and mitigations. So the first one is generally neighbor discovery protocol. Anybody can send a neighbor advertisement or a router advertisement. And generally, so you could then therefore either spoof some other host by sending out a neighbor advertisement saying, I am that host, or spoof the router and perpetrate a man-in-the-middle attack by saying, I'm the router, send all traffic to me. That's not necessarily significantly worse than various kinds of ARP attacks or other things that can happen in IPv4, but it is something we really do want to pay attention to. And there's been a significant amount of work in in what these kinds of attacks look like and how to mitigate against them. Essentially, it's I'm this host. No, I'm this host. One of the related issues is a cache table exhaustion attack, where you've got a list of, in v4 it would have been the ARP table. You've got a list of MAC addresses and IP addresses. In v6 it's the same thing. It's MAC addresses and IP addresses. It's the neighbor table. Then I'm going to come back to that in a minute, actually. Yeah. So there's actually, this is an ongoing argument at the IETF. And I have not figured, even though I've tried, I've not figured out a resolution. There's some religion about Slack versus DHCPv6. A lot of network operators specifically say, we must use DHCPv6 because we don't want to have to figure out new things. We use DHCP in IPv4, It's why should we change our business models, our technology models, just because we're using a new protocol? That doesn't make any sense. Let us use what we're used to. And I'm sympathetic to that argument. Let's not make things more complicated than they need to be. Let's not require people to do new things because that just adds resistance to deploying IPv6. The trouble is, and people will then say, if you say, but okay, why DHCP instead of just using Slack for addressing? And the very common answer, especially among enterprise network operators, is, well, when I do DHCP, I then get a log. I can see who's attached to my network. Well, I don't know if you've ever had this problem in your own networks, but when I was working in an enterprise network specifically, one of the things I was constantly worried about was somebody attaching a device to my network and me not knowing about it. Because even though we were using DHCP in IPv4, you could connect a device and just either the DHCP server would answer, or you could just manually configure an address. Look at the address of a device already on the network and configure another address. Boom, you're on the network. And I don't have it in my DHCP logs. So DHCP isn't providing you any additional security by having that logging. On the other hand, Slack is great. I mean, it's trivial, it's easy, but if you need any more configuration information than IP address, netmask, and name server, you're not going to get it from from RAs. So the mitigations, good. I did include that in this slide. So basic mitigations. We talked a little bit yesterday about EAP and 802.1x using EAP as part of its authentication mechanism, so that you're not allowed to actually connect to the network until you have been. And there are lots of different ways to implement it, but essentially, you only allow devices on the network that have been authorized. It's it's I'm not going to say it's a heavyweight protocol. Because for the amount of security you get for it, I think it's pretty reasonable. But it does require some development and training. And it's not, and I'm thinking here about data center networks and enterprise networks. A mobile network or an ISP, sort of a different kind of network. You're not worried about rogue attachments. You've got home users. You have your own mechanisms there. So 802.1x, highly recommended. It works and completely mitigates the rogue device attaching to your network risk. You can also, and I do suggest, logging the neighbor discovery tables. So whatever, you go onto the routers, and either every time there's a new entry in your neighbor discovery table, either send a syslog message or pull an SNMP or use netconf and pull, and there is a Yang model for the neighbor table. Basically whatever you use to track things on your network, that mechanism will work for this. And then you can do some kind of logic on the back end to say, is this a device that I recognize? And only authorize, or throw an alarm if it's a device that you don't recognize by MAC address. Smurf attacks, where you're spoofing somebody else's address on the network and sending things that have to go to everybody on the network. We don't have broadcast addresses in v6. We have multicast addresses. And early on, people said, great, we have multicast, no more Smurf attacks. Well, sure, but if the first one on here, FF01::1, is the all nodes multicast address. You send a packet to that, it's going to all nodes on the network. Everybody has to receive it. If you send a packet from that address, then everybody's going to have to respond to that. So the potential still exists. And then all of the other potential multicast addresses. And these are just some of the well-known multicast addresses. The full list is at the URL there. Okay, so I talked a little bit about neighbor table exhaustion. Here's how that works. You've got a device that's sending out a neighbor solicitation. Who has address 2001:DB8::1? And that goes out to the network. And so the router says, I don't know who that is, but I'm going to go ahead and open a pending entry saying, I'm waiting for a response to find out who has this address. And then at the same time that's opening that, the querying device will send another packet, another neighbor solicitation saying who has that address, ::2. And so then we add a new entry. And then it keeps doing that over and over and over, all the way up through all ones, the full number of possible addresses. Clearly, you're going to have a cache exhaustion by then. Yes, sir?
Who owns this 2001:DB8 address that you keep using here?
Michael Richardson asks, because the mic wasn't working, I'm going to repeat his question, who owns to this 2001:DB8 prefix that I keep referring to. That is the official documentation prefix in IPv6, which is why I keep using 2001:DB8 for all my examples. Just like in my IPv4 examples, the few that I have, I use 192.0.2 because that is /24, because that is the official documentation prefix for IPv4. Oh, did you want a sticker? You already have. You're all the way back to me. You can get one later. So, and the worst part is you don't have to be on the local network to launch this kind of attack. This could happen outside the network if you don't have the right mitigations in place. That's pretty grim, and that was something that was sort of lit some fires under some people to think more seriously about security probably 7 or 8 years ago at the IETF. We suddenly realized this was a significant vulnerability. If you weren't going to deploy IPv6 in your data center if somebody could launch a simple packet attack like this from their cell phone and bring down your data center. That's probably not a good idea. So, oh, and there's one more version of this that I love mostly because of its name, the ping pong attack, where if you have a point-to-point network between two routers numbered out of a /64, all you have to do is send a ping to any address that's not one of those two devices. And the router on the right will get the packet and say, oh, this is a directly attached network, but it's not my address. Back out. And the packet on the left will receive that packet and say, oh, it's directly attached, but it's not my address. I need to send it back out the network to see where this ping goes. And so that'll go back and forth until your TTL expires. But then again, that's TTL of 30. It's going to keep going, and you can absolutely flood the table that way. Simple mitigations. For that one, just use a /127 net mask. Actually, the best recommendation is generally to reserve a /64 for each point-to-point link on your network, but actually configure a /127. That way, there's no unused address that could be bounced back and forth. But you're also not messing with allocations, with strange subnet lanes. You've got plenty of addresses. Don't worry about burning a /64, even though you're only using a 127. Just that's fine. That's considered best practice, and that's why we've got documents. We've got documents describing those best practices. You can, of course, anything that's unused, in particular, unused on the rest of your network, just put an ACL on that so that you don't have unused space that you need to, that's going to send packets. You don't have, and you can't receive packets destined for unused space. You can do a queue, rate limit your queues. So some devices will have separate queues for refreshing known neighbor table entries, and a separate queue for discovering new neighbor table entries. So if you have separate queues for that, then you can actually rate limit the difference and say, okay, we're only going to allow so many discoveries, so many open pending discoveries at a time for new, but anything that's already existing that we have a good value for, a good entry for, let it go, because that's, clearly we know there is a device with that number. That's a pretty good one. You can always rate limit ICMP, of course, and then I talked about ways to, log bad neighbor discovery, either packets, protocol packets or anything else. And of course, another RFC with more best practices. Further mitigations. Has anybody ever seen send in the wild, secure neighbor discovery? I've never seen it in the wild. I've never heard of it actually being used. But people always talk about it, and so I feel like a discussion of security in IPv6 isn't complete unless I've mentioned it and described it. I think the reason I've never seen it in the wild, the way it basically works is you have a certificated neighbor discovery protocol. You're only allowed to send, well, people will only receive neighbor discovery protocol packets that have a certificate attached to them. Okay, so if it has a certificate, then you have to go check with the certificate authority to see if it's a valid certificate. But if you have to check with the CA, then you need to know that your path to the certificate authority is actually valid, which means you have to have a chain of send-enabled paths all the way up to your CA, unless your CA is local. Yes, sir. What's your name again?
My name's Michael Richardson. It's so sad that we couldn't do send properly with IPsec, but and we're very close to being able to do it. And it was an IPsec bug that prevented it. But the same reason why we don't have IPsec everywhere is the same reason we don't have send everywhere, which is we don't have certificates everywhere.
Yeah.
Insert my talk from yesterday. right? So that's one of the key things, is that we don't have secure enrollment. We have no identities that are reasonable on any host. And, you know, rather than being sad about this situation, and we should have fixed this at the beginning, and we should have fixed email to not have spam, right? The fact that we have a successful internet that has grown this big is in fact due to the fact that we didn't need you to get authorization to be on the network. But now we need it. So, you know, as I said, send and AH and IPsec, you know, will suddenly become useful when we have a reasonable expectation that every device has an identity that you can read it, make a trust path to. Right. And that doesn't have to be 100% of the devices. It could be only 6% of the devices, and it could be really, really useful. So I still have some hope. We have to fix the SHA-1 and the CGA and maybe the patent on that stuff will expire by the time we actually use it. But, you know, I'm still hopeful that it'll happen. And I think that the interesting part is that particularly in networks, like ISP access networks, like, you know, cable companies run, because the DSLs don't use neighbor discovery anyway, essentially. This suddenly becomes really, really useful. You can really know who your customers are, and you can keep them from actually impersonating each other in a meaningful way. So I think that's really useful in the future, but I think you should keep talking about send every time you do an IPv6 talk.
So my impression of send right now is completely consistent with yours, which is that it's a heavyweight solution to a problem that doesn't seem bad enough to warrant it right now.
Exactly, exactly. And if you cared that much, you'd probably lock your whole wired network down with 1X and MAC address stuff. And it's a real hack, and it layer violates all up and down, and it's hard to do. But if you really cared about it, that's probably what you would do now. And you do that because no one supports send, right? And no one's going to support send until someone who has that requirement comes along and says, I'm tired of doing MAC address wiring. I want you to implement send. Well, and they're big enough to make it happen. And I don't know who that's going to be anymore, because I don't think it's going to be the US DoD or something. But
and the network admission and control sort of implementations or fixtures that go along or that can be done with 802.1x say, you can also, as part of your authentication, require a certificate to be presented by the client, and then go check that against whatever your internal system is.
Right, and in fact, it's only scalable if you do it that way. Right. So
it's not. So you're not dependent on MAC address. I mean, you could also do it based on MAC address. You can have a central table.
Oh, no, but after the 1X certificate exchange happens, the silicon locks you down by MAC address.
Oh, right.
Right, okay. The point is that the admission at gigabit speeds is not going to be on certificates. It's going to be on MAC addresses, right? So, and you're going to have a non-learning switch. Right? That's part of the other point, because, you know, you need to turn off stuff. And I tried to build a non-learning switch with Open vSwitch a couple months ago.
Oh, fine.
Yeah. And it was remarkably hard because I couldn't do it. I couldn't find the right code to comment out to make it not learn, because all the examples said, and then you want to go through the learning table. And I said, no, I don't want to go through the learning table. I want to manually add things. And I couldn't find the API to manually add things. I could only find the API to automatically add things. And I'm sure it's just ignorance. But, you know, I was sort of like, this should be an easy thing to make a stupider switch rather than a smarter one.
Astonishing how hard manual is, right?
Yeah. So anyway, I think you should keep talking about it, and I think you should tell people why it's not happening, which is you need a cert. Yeah.
You need a cert. And so you need to issue a cert. You need to have a certificate authority that you can check. You need to trust the path in between, which is, it's not rocket science, but it's a lot for a network engineer who's doing, you know, edge access control. That's, you know, and you know, and so there are other things, other mitigations too. So I'm gonna move on.
So there's a lot of.
I am talking about it, by the way.
There was a lot of interesting drafts by what's her name, Sarah, on the problems with CGA. I can't remember her last name, Hussein or something like this, and there's both a sociological and IETF cultural thing to understand in why some of her work. She's at Huawei. She works at Huawei. Very, very determined person, but she gave up, and partly it was reasonable because She was trying to fix a problem that today no one has because no one's using CGA. And unfortunately, she was got to the point of annoying people.
Right.
Okay, and this is unfortunate because the ideas were really good. Just, you know, she was really wanted to get a draft published.
Right.
Right, and she was under a lot of pressure, it seemed, to do something like this. And so it was a way of it was a good treatise in how a well-meaning person can go who has really smart, good ideas, can go afoul of the IETF process unintentionally, you know. And it's too bad that happened, and I don't know that we'll ever see her again. So at the IETF, that is.
So I think it's worth doing, since this is IESOC, I think it's worth spending a little more time on that, if it's okay with you. Because what I want to, okay, rather than scare everybody here about the unintended IETF confrontations, can you talk more about what kinds of things people ought to be thinking about? Not necessarily because I don't want to.
Well, I think that the critical thing is it's not unreasonable for a document, particularly a 0.0 document, to spend 2 or 3 pages of I'm going to say well-written English, and that may, if you're not an English speaker or if you are, you know, from a North American school system, you're an incompetent English speaker, okay? Most of us are, you know, most of us have to learn. We had to have things beaten into us in grade 10 or 11 about how to write an actual essay, and a lot of us didn't learn it, right? So we could talk a lot about what that means, but I'll skip from that. But it's reasonable to have several pages of really well-written text, reviewed text, that just explains the problem you're trying to solve. And it's okay if under the solution part, protocol details, right, if you go by the RFC 791 template, okay, of how you do things, not everyone likes 791. That's, you know, it's John Postel did a really good job, but not everyone likes his description, and that's why there's, you know, 19 books out there on explaining TCP/IP, right? And we don't give 791 to students in second year. We give them a textbook that has, you know, so you have to distinguish between a good protocol description and a good tutorial, right? Anyway, but it's okay if under protocol details it says to be TBD in a 0.0 draft, because the point is not to tell people what the solution is. The point is to get people to agree that the problem, as you've described, is a real problem. It's worth solving, okay? And only after they have those 2 points agreed upon do you tell them, and this is what it costs to solve it. Because you have to basically get people to agree that they would be willing to pay something, I don't mean money, I mean bits on the wire, code space, effort, whatever, to solve this problem. You essentially have to convince them the sky is falling if you don't solve this.
So sometimes a document like that is just a problem statement document.
And sometimes it's just a problem statement.
And that may be a separate thing. If you already have ideas about solution space, absolutely, at least sketch them in and say here's one possible solution. Or if you have 3 possible solutions, describe those and let the IETF talk about the trade-offs between them. That's a great place to be.
And it's a great, and the catch is, actually I prefer it if you have 3 solutions in a 0.0 document, personal 0.0 document, because it tells me that you're not particularly attached to any one.
Exactly.
You're not pushing a particular way of doing it. You're open to feedback, okay? And it's possible that someone will say, look, you've come up with a really interesting observation that this is happening, but I'm not convinced it's a problem for the reason you said.
Sure.
It's a problem, but not for the reason you said. And therefore, the solution trade-offs, because there's trade-offs in the solution that you have, the solution that you are going to propose, maybe it's a different trade-off because you've pointed out there's a real issue here, right? And the solution maybe someone says, and because it's a bigger problem than you thought, I'm willing to pay more.
Yes.
Right? So that's my take on it.
Let's carry on.
Hi, myself Shibu Piriyat. I work in IPsec in Juniper. So my question is related to...
Are you okay?
He said, I work in IPv6 for Juniper, and Michael said, do you need a hug?
Yeah, so the question is something related to MTU, fragmentation.
Yeah.
So in IPv6, you say middle boxes cannot fragment and reassemble, and path-MTUD is actually enforced. So the question is, when it comes to ECMP multipaths, right? So is it a theoretical thing, or it's a reality that the paths will change on a flow? Because the flows are like the mobile app-based, right? They are always on. So the flow life is kind of longer as compared to the real browsing one. So the paths in technicality can change.
Yep.
So the MTU can change, and the middle box cannot fragment. So what about the user experience?
So what was the last one?
What about the user experience,
So what about the
right?
user
The packets can get dropped if it enters into another path where the MTU is smaller.
So, but still, whenever a packet gets dropped because of an MTU mismatch, because the new MTU is smaller, anytime you drop that packet because of packet size, you would send an ICMP packet too big message.
But
So
that's unauthenticated.
But that's what?
That is unauthenticated. Anyone
Yes,
can.
it absolutely is
anyone
unauthenticated. You're right. That's a good point. It's unauthenticated. Anybody could send. Let me see how this goes. So I'm trying to think of the attack vector. Anybody on the internet could send you a packet too big message originated from some address along the path. Yes, that could happen.
Yeah.
And it could be packet too big, reduce your MTU to 10 bytes.
Exactly.
Or maybe 50 bytes because it has to be minimum packet size.
Minimum, yeah. 1280 maybe. So I mean, this is, I think, a gray area. I feel the different pieces of RFCs are not connected well each other, right?
Yeah.
There is a black spot.
That's a really interesting vector that I haven't heard anybody else describe before. So yes.
So I tried proposing a solution from the IPsec point of view in IPsec ME.
Mm-hmm.
So I mean, so it's more of IPsec ME mostly look into the crypto aspect and don't really understand the network aspect of it. So so they feel that ECMP is not a real thing.
They feel that ECMP is a real thing?
Not a real thing.
It's not a real thing. Wait, what? How many people in the room have a network that has ECMP on it? All right, so not that. Oh, look at there. So okay, we've got at least 5 people in the room. There you go. It's a real thing. 10% of the room has is running ECMP someplace.
So yeah, being a developer, we kind of experiment. I mean, kind of not get enough exposure to the field, right? So we can't actually go and say, no, look, these are all the ECMPs available. So we kind of go on the back foot. But I think this is a real point where there is a fix is needed. So another aspect of what we see from the IPsec point of view is NAT traversal. Mm-hmm. So what is the official position from IETF when it comes to IPv6 and NAT? Can't you just mandate something like don't fragment on the middle router, so don't NAT? So
there's at least one document, I don't remember which one off the top of my head, that has a strong recommendation against NAT in IPv6 for a whole variety of reasons.
Right.
And there's a nuance between address sharing NAT and network prefix translation, but in both cases it's pretty strongly recommended against for a whole variety of documented reasons. There have been some movements, frequently somebody will come up with a draft that's not frequently, every couple of years somebody comes up with a draft that says, hey, we have unique local addressing, which means you can have a /48 that's unique around the world, but shouldn't be publicly routed, and you can use that for whatever you want to. And somebody will say, no, you absolutely cannot use ULA. We must say use of those addresses is evil, because if you use ULA, we're sure you're eventually going to do prefix translation and use NAT on the network. My position has always been, you can't say something is evil in an internet draft. That's not the way it works. We can say, is not recommended for the following reasons, or even is not recommended for the reasons very well documented in this other document. But we can't just say, you must never ever do this because, especially when some people are saying, I have valid use cases for this. So, summary answer, the IETF has said we recommend against the use of NAT in IPv6, but it's a recommendation. We're not the common phrase. We're not the protocol police. We can't stop you from doing anything particular.
Yeah. So what security actually it adds to? That's what I was thinking. Except from the hiding the IP address part. Maybe that's only one, but does it really give a security? It's kind of obscuration.
No, I think that other than potentially hiding endpoints, I don't think anybody thinks it's, especially with network prefix translation, which is a one-to-one mapping, and so there's no stateful mapping at all. There's no security benefit to it.
Especially when it comes to IPsec, we have this NAT problem, and entire control traffic as well as the data traffic becomes a one single fat pipe. Now you lose entropy. Now you have to put UDP encapsulation for that to retain the entropy. So all those things just to cater something which is not an existing thing.
And my humble opinion has been that all of the mechanisms to do NAT traversal, ice, stun, turn, all of that stuff is heavyweight, it's cumbersome, it's a lot of work. And if people would just deploy IPv6, you wouldn't need it anymore. IPv6 with a stateful firewall, absolutely, and let the firewall administrator decide whether you want to allow the encrypted traffic. That's a policy matter. But let's get rid of all this heavyweight junk. And that's part of the reason, actually, Nalini mentioned my draft to declare v4 historic, is part of what I wanted to do is say, let's stop spending IETF time and effort on NAT traversal techniques when we're trying to get rid of NAT because we're trying to get to IPv6 where we don't need NAT anymore. Right. But it didn't find consensus because it's too soon, Lee. At the time, 80% of the internet is still on IPv4. Okay, well now it's 75%. When do we bring it up again?
Okay. Thank you.
Hi. I'm Guru Prasad from Cisco. So I just want to understand which scenarios you suggest Slack and which scenarios stateful. So can if I want address to be configured, controlled from the cloud, I don't think I can have a Slack. What is your answer?
If you want it controlled from the cloud, no, not really. Unless you have some kind of policy control over the host itself, where you can tell the host how to derive its Slack-based address.
So I feel Slack is not that effective compared to DHCP6, right?
It's not that difficult, is that what you said?
Not that effective. I mean,
effective.
Because DHCP6 we can place anywhere in the internet. Whereas Slack means it should be within the L2 only.
Right.
We use link local addresses.
Well, I mean, it sort of depends on what kind of network you're talking about. I would not use Slack.
I have a huge campus of a couple of buildings, each building having 1,000 nodes.
Okay, so I think it still depends. Well, let me back up. The easy case is coffee shop Wi-Fi, Slack. I mean, there's just
Slack.
why do anything more complicated than that?
Okay.
Enterprise network, enterprise campus or university with lots of different buildings. Do you really need centralization? If all you want to do is log the mapping, then log that from the router.
Because I need to have RAs configured at every router connecting a line segment.
But that's
managing that would be cumbersome for a big campus, right?
RAs are on automatically on every router in v6.
Pardon?
And router advertisements are automatically enabled on every IPv6 router. You can't route without them.
But because I need to configure the prefixes that host can take. Like I need to monitor and manage in case of Slack.
So this is part of the.
What is your suggestion? Can I go for DHCP6?
This is part of the religious argument.
Okay.
And I think this is religious. I don't think this is a compelling argument. Part of the argument is DHCP says I have a strong central management system and I control everything from a central infrastructure and I have a database of who should get what addresses.
Right.
Slack says the router is authoritative for what it routes. Okay. And if the router is misconfigured, it's not going to work anyway. So the router can tell you what prefix it's going to route traffic to, and then you can choose an address from that prefix.
Okay.
There was a concern in development of the protocols that your DHCP table or database might fall out of sync with your actual router infrastructure. Now, in my opinion, we don't have that problem very often in IPv4 because it's very easy to tell that nothing's working. If you're giving addresses that can't be routed, you figure that out pretty quickly. But so that's the argument for why you might might use Slack instead of DHCP. My general guidance is to say, I do think that Slack is easier because it's automatically on. There's no additional configuration. You don't have to run any daemons unless you're trying to do logging.
Okay.
Or you must, if you want any additional configuration, like go find an additional configuration file or use these options or use the following transition technologies. All of those are configuration options that can only be sent through DHCP. There's no mechanism for them in
Another
RA.
question is related to this Slack. Like we are talking about security. Like Slack is within the L2. So do we worry so much within L2? When we have to cross our network using L3, then we have to be cautious. So we are talk so much about security, you know. So directly I can use Slack with bare NS, ND, RA messages without any encryption or decryption, right? That should be fine, no?
It may depend on the topology of your L2 network. If you have a wired L2 network with switching control that you don't allow devices to send to each other until they've been authenticated on the network, absolutely. That's, that if you're in a Wi-Fi environment where it's wide open, it's a different L2 kind of environment.
Yeah, okay, thanks.
Sure.
Good morning, Lee.
Good morning.
This is Ramesh from Geo. So I have a basic fundamental question. We have seen like there are certain standard practices and certain recommendations for best use of the IPv6 address. Point-to-point link, we talk about /127 because only 2 are used. Why to waste additional resources, right? So when you look at this, compare with the IP address which we assign to the mobile device, okay, which is /64. And we know that any device, whether we use Slack or in fact now further IP allocation to the other device in the teething mode, there will always be a limited number of devices. There will not be a situation we need like trillions of IP addresses or devices connecting mobile device. And why do we have that recommendation of /64 for mobile device where we know we will always have a limited number of devices?
Right.
And I don't think there is an attempt that, okay, we will be using MAC addresses for further allocation of IP addresses to the teething devices.
So my understanding, and I wasn't there at the time that IPv6 was being developed. I was still, when the IPv6 protocols were being developed, I was still working on Novell IPX networks. So my understanding at the time was that there were multiple competing protocol or address protocol alternatives that were being debated. And people talked about, similar to the old ATM wars about the cell size. Do we want, 32 bits isn't enough. Do we want 48 bits, 64 bits, 96? How many bits do we need? How do we make the addresses longer? And how do we make sure we don't run out? And the people said, you know what, it's, we've got 64-bit CPUs now, let's do 64-bit addresses. And then almost to the last minute, somebody came in and said, what would be cool is if we could add another 64 bits. And I think there was some idea at the time that we would have a locator identifier split, whether it was Lisp or ILNP or other system there, so that you would only need to know about the first 64 bits to move anything out on the internet. And the last 64 bits were just sort of free bits that you could play with in host addressing. That's kind of my understanding. And I will point out, because is it the right decision? I really can't defend the decision. It's the decision that was made. In most systems, I think there is an RFC now, and I don't remember which one it is, but I think there is one that says that we can, that the /64 boundary is arbitrary, and you shouldn't hard code an assumption of /64 into anything you do. You should use it as a best practice, but if you want to route on a /96 or do something else in your configuration in your network, that's up to you. Your devices should allow it. Having said that, I also feel compelled to point out that 2001/3 is only the first 2000, whatever the 2000/3? I forget what it is. So we've only done 1/8 of the IPv6 address space in this protocol. So so if we've screwed it up 50 years from now, when we allocate the next block of IPv6 address space, we can make different assumptions. Supposedly. I know it's harder to tighten the belt than to loosen the belt. So I think that's my answer to your question. It's not an authoritative answer, but that's why we have the /64 boundary.
Yeah, look.
I think.
Michael Richardson here. I'll just add that my first IETF meeting, I went to the Ipv6 working group, and the contentious topic on the floor at the very last minute, the document was not yet published, was should we swap the location of the source and destination addresses in the packet? Okay. The argument was, because right now it's source address, then destination address. The argument was that when you looked at the number of bits and you looked at cache fills on processors, you only need the first 64 bits of the destination address, and processors had 128-bit wide caches. In the first cache hit miss, you would get the destination address and never look at the rest of the packet. Benefit, right?
Yeah.
Okay, major benefit, as opposed to 2 cache line hits to get the thing. And they point, someone else pointed, well, on processors, MIPS 32s, which were common in routers at the time, with 64-bit cache misses, by the time you actually looked at the first 8 bytes to find out that it was V6, the other ones, other cache lines have probably already filled, and so it's a moot point. It's only on the more expensive 128-bit processors that you get the speed up, right? And so there was a great debate in the room about whether this was worth doing at the last moment. And Christian Wiedema says, well, of course, I have to let you know that I am in favor of this. And they all looked at him like, what? He says, all of the copies of my book will be obsolete and you'll all have to buy new ones. and then the decision was made to just stick with what we had, right? Because 256-bit cache lines were coming, and then it was a moot point, right?
One of the amazing things about the IETF is sitting next to somebody like Christian Wiedema, whose book was my authoritative text for years, sitting next to him at a working group meeting and going, oh my gosh, that's Christian Wiedema. And then he gets up a microphone and I go, oh my God, he's wrong. I have to go to the microphone and tell him he's wrong. And he's I totally disagree with you. And you know, no arrogance. That's the way it is. There's so many idols that I have that I've met at the IETF where they have no arrogance at all and are perfectly happy to have a debate with me, and they don't look at me as somebody new and who are you, you little pipsqueak. Please, go ahead, Nalini, whatever your name is.
Nalini Elkins. You know, I'm going to make a meta comment. I mean, if you find yourself unable to sit still and feel yourself like, I have to get into this argument here, then you belong at the IETF.
Yes.
So having said that, we totally need to do a whole thing on address planning and what people do, because I'm just going to give you a couple things. And this is a totally religious argument, the DHCP and, you know, and /64, not /64. But I'm going to tell you a couple of things that real enterprises, fortunately or unfortunately, do with address planning is they'll take like a bit here or a bit there and say that stands for printer, or you know. And I'm not saying that's good or bad. I'm just saying that's the reality of what happens, and you're not going to be able to do that without DHCP.
Oh, right.
Yeah. I mean, so there you are. And if it's inside your network, well, then there you are. And I'm going to throw one thing in. One of the things that seriously bothers me is the lack of crypto agility that there is at enterprises. I mean, it takes us 20 years to change, you know, to do something like, I mean, you know, it's like we cannot do this. So if you did know what a device was, there is something to be said for, you know, being able to swap out the crypto on it. So just throwing that out.
Hi.
Hi.
Kailash here. I have a slightly different take on it. Actually, I was wondering on, you know, I've been working on infrastructure for some time. Yeah. Yesterday I was talking to you about IPv6 and Azure and all that.
Yeah.
So we had a myth being in the fraternity group, you know, saying the performance of IPv4 versus IPv6, you know. We had a lot of debates on that. IPv4, slow, IPv6, faster, simplified routing. Others says no, there are only few routers supporting it. There are only few hops, paths available, so it's actually slower. So I thought, let me, you know, understand your take on it. Yeah.
I actually have a 40-minute
performance. I tried doing that as well, and it was nearly equal as well. I tried.
Yeah. Anything I've done in the lab shows them to be absolutely identical in performance.
Google and a couple of things I tried nearly identical, but sometimes IPv6 is slower as well.
Right.
I've seen that. Yeah.
So in the lab, the performance is identical. In the real world, the performance varies. It usually, from what the measurements, I've got a 40-minute talk on this because I've got a dozen sources. It usually varies such that IPv6 is observed to be faster, lower latency, shorter round trip times. That is, however, actually I was talking to somebody yesterday about this is an area ripe for research, I think.
Yeah.
Jeff Houston, in addition to the numbers that I think many of you have seen about IPv6 adoption,
Yeah.
also has IPv6 performance numbers on the same APNIC page, where he's doing in the same, his experiment is he serves up ads through Google DoubleClick, and when you get the ad, it fetches, it goes and grabs a URL that's IPv4 only and a URL that's IPv6 only, and because he can see the SYN and send a SYN-ACK and wait for the ACK, but the time between the SYN-ACK and the ACK is one round trip time. So he knows the round trip time for v4 and the round trip time for v6 and can compare those and tell us which one's faster. And since they're being served, that's a unique URL in both cases, it's being served from the same device, and therefore he knows it's coming from the same device at the same time, and they're comparable. What he finds is, I forgot to look this up for India this morning, in the US, on average, IPv6 is 10 milliseconds faster.
Okay.
And I think that's true in India as well. I think it's about 10 milliseconds.
I tried doing it from Ericsson labs.
Yeah.
I found mixed results. Sometimes it was slower, sometimes it's...
So
I could not conclude anything.
I have a couple of theories. One is, when I was at Time Warner Cable, I said, this is crazy. I need to understand the performance, and I need to be able to report to my executives that we're not ruining the customer experience.
Exactly. Yeah, that was my point, right? Actually. Yeah.
So I put probes into about a dozen different hubs that were, we've got, right one step above the access edge. So in the same hub, that were doing TCP, SYN-ACK, same kind of connections to 20 different common websites and comparing the v4, v6 performance. On average, v6 was faster for us.
Okay.
Sometimes v4 was faster. We also then would do a trace route on both v4 and v6. We found that generally they were pretty close. Sometimes we could see that the v6 path was shorter, but it was because it was being tunneled over something somewhere along the path. There was a tunnel, therefore some hops were being obscured. The biggest thing that we found was that when our backbone engineers or our network engineers were doing traffic engineering in operations, we've got a congested port. Move some traffic to a different port that's not congested. They would usually move the v4 traffic only and leave the v6 traffic where it was.
Yeah.
Because most of the traffic was v4. And then the v6 traffic is taking the best path, and the v4 traffic is taking some alternate path that's uncongested. And therefore,
faster,
now it's faster. But sometimes they would remember to move both, and then when this port became less saturated, they would forget to move both protocols back, and so v6 would continue taking the less optimal path. That's one thing. Another thing, theory that I haven't been able to test it rigorously, is that, depending on, mobile networks in particular, most of the world is mobile. Mobile networks have several options for how to deploy IPv6.
Yeah.
They can do a v6 only APN or a dual stack APN. Yeah. When I've tried to look at how different mobile networks perform, what I've found is that dual stack APNs are pretty much exactly the same in terms of performance.
Okay.
v6 only APNs have a slightly faster v6 performance, and I think it's because, I think that Jeff Houston's numbers, I think it's because it's for in Android phones. So all apps for Apple must certify they've been tested in at least a NAT6.4 environment. So you can't have v4 literals. You can't work on an Apple phone if you don't support IPv6, theoretically. But in Android, they said, yeah, that's great, Apple. We don't have that kind of control over our app developers. So they put an XLAT, a v4 to v6 translator, in the handset, which means that if you're using a v4 literal or otherwise require v4 in the local app, the handset's doing the translation from v4 to v6. And I think the handset is actually slow at doing that translation.
Yeah, yeah.
It's not optimized for packet header translation. So I think that's probably where the latency is being added for IPv4. Yeah. Oh, good. I was hoping that you'd get up and
Just one more related question, whether it's slow or fast.
Yeah.
See, look at the dual stack device. So one school of thought is that any device where a dual stack, if there is any HTTP packet generated, it has to send the DNS request. Mm-hmm. So one school of thought is that it is sending both for A and quad A record DNS request at the same time. Okay, if it is sending the same time, we hope the transport network is same. Okay, there is no latency. It is hitting the DNS at the same time, and assuming DNS is also responding both queries at the same time. Response comes to the device. Now, device has to choose whether it should use IPv6 stack, okay, or it should use IPv4 stack.
Right.
So one side, one school of thought is that yes, it prefers IPv6. We are not really clear what is the mechanism work in the device or in the operating system where it prefers the IPv6.
Right.
Okay.
So you're familiar with the Happy Eyeballs algorithm? So so the IETF standardized, as we said, IETF said we can't ruin user experience. We need to make sure that if either IPv4 or IPv6 is a terrible experience, that we're going to fall back quickly to the other address family. And then just last year, I think, there was an updated version based on statistics gathered by Apple and others saying, we can tweak some of the timers and some of the algorithms. And I don't remember the full, I've got it in a different presentation, but it's something like, so one of the problems was that they were sending, bad user experience, many devices would send a single DNS query with both an A record and a quad A record response. And they wouldn't get, with query, and they wouldn't get a response until the resolver had timed out on one of them. And so you might have to wait 3 seconds before you even got a DNS response. Or the device might be smarter and send 2 DNS queries, one for A record and one for quad A record, and then wait until they got both responses before actually initiating a session. Also a bad experience. If you've got a DNS record, then start doing, then go on to the next step in establishing a connection. So that's what's supposed to happen now in most devices. And then there are more steps and there are timers in there. And it's something like, because you might not have a quad A record in the resolver cache, give it a 50 millisecond head start, I think is what they say. And then once you have that, once you get a quad A response, go ahead and fire off the actual session initiation. If you get a V4 response first, wait a little bit before starting that session. And once you've started one, don't switch to another one. Just keep using what you're using, unless your session establishment fails, in which case start interleaving responses as you get them to see, so that you've got a path to get to whatever actually works. That's what's supposed to happen, but I don't know what actually happens in devices.
Yeah, second case is like where it is sending only for the quad A first, waiting for the response. If no response, then we start IPv4. Definitely there is an impact on the customer experience because he has to wait. And that is going to be significant enough. So that is definitely not a very good option to even adopt in the industry. Another thing which we are discussing, like whether IPv6 faster or slower, what we assume, like because of the simplified header in IPv6, when it's passing through the multiple hops, maybe because of simplicity, lesser number of fields need to look at it. It may be few microseconds faster in terms of processing the packet header and sending to that.
That is one school of thought.
There is only one school of thought. However, transport network remains same, and we assume the links are not slow; it's faster, so there is no congestion.
Right.
Okay. So if there is no congestion, transport latency or propagation delay, the physics remain same.
Right.
Only the processing will make the difference. Right.
Yep. And that's in my list of theories that I haven't figured out how to test it and prove it. Because you're right, if it's a simpler, well, it's also, if you have 2 paths through a network, only your newer equipment is going to support IPv6, and therefore the IPv6 path is going to take the newest equipment. It's going to be faster. And also, one of the great things about IPv6 is you get your large v6 allocation, and you don't keep getting additional prefixes, every few months or every year or two. And so your ACLs are 3 lines long instead of 2,000 lines long. And so processing through your ACLs is faster. All of those things, again, I've never been able to prove any performance difference in the lab because it's a lab environment. And even those kinds of tests, I can't measure microseconds of latency through each hop. But if you add 100 If you add 100 microseconds of latency times 10 hops, that's a millisecond.
Yeah. We also attempted to test it, but we could not figure out really the difference between the two. Because of the variation in the results, in fact, when we repeat the test and we find slightly variations.
So yeah, unfortunately, like, as I've said, I think this is an area ripe for research. All right, fantastic. I have 40 more slides to go through in 14 minutes. This is great. I think this is an excellent use of time, but I'm going to, and I do want to keep sort of talk about some of the things that I was actually asked to talk about. Okay, we've talked about send. RA guard basically tells the switch to pay attention to what router advertisements it receives from where, and only allow the ones that are known to be good. Savvy, source address verification, says figure out which source address is true and don't allow packets inbound from a bad source address. And there's a couple of different algorithms there. That was a whole working group. So rather than listing one RFC, I've just given you a pointer to the working group. That'd be a great place to get involved if it were still active, but they finished their work a few years ago. Okay, that was the local area networks. We're going to talk about global risks. We've probably already hit on a couple of these. I have anecdotal data. I don't have data. But when you connect to a VPN, the idea is you connect your device, your laptop, whatever, to a local network, and you fire up a VPN that establishes an encrypted tunnel to a firewall in your probably corporate network. And the firewall does whatever security filtering is appropriate and then sends the traffic out to the rest of the internet. There are VPN clients in the wild. I have actually had clients say, oh my gosh, you're kidding, that's actually happening to us. Where if you connect your device to a dual stack network, the VPN client is unaware of IPv6, doesn't examine it. So the V4 traffic goes through the VPN. The V6 traffic goes out on the internet. You have a split tunnel, your security policy is completely gone. It can be even worse because you could do a DNS query and get a quad A record and try to use it, but your VPN client sort of understands V6, and so it says so you're trying to use this address, but you're not allowed to because traffic's only allowed to go through the VPN client, but there's no V6 on the VPN client, so you just drop dead. You can't get to Google or Facebook or Wikipedia or anything that has V6. Even worse is if you're behind an ISP, including some mobile networks where they're doing DNS 6.4 and you only get a quad A record and your VPN client speaks V4. I'll talk about that a little bit in enterprise experiences this afternoon. We talked a little bit about fragmentation. So actually, it's a potential denial of service. If you can send a whole bunch of fragments because you're only allowed to do fragmentation at endpoints, we talked about it a little bit already. There's potential problems there along the path. It's a good place to troubleshoot, by the way. If things are broken in V6, go look for path MTU errors, go look for fragmentation. Specifically in firewalls, I'm not going to go through all of the extension headers. The extension headers are one of the coolest things in IPv6 that enable some really interesting new capabilities, many of which aren't being used, but there's a lot of possibilities. We've got, go ahead.
Sorry, I don't mean to. I would say ICMP, there's lots of things that are eating it still, unfortunately, including in the Linux kernel.
Yeah.
One-armed router, such as a VPN termination point on Linux, will not send ICMPs out because they appear to be going out the same interface the packet came in, even though it's actually a virtual interface, but that's because the IPsec guys, I can't say bad enough things about what they did, but anyway. However, there is a syscontrol, which is buried in IPv4 TCP sysctls, but it affects TCP on V6 as well, which enables PLPMTU for IPv6, and it works great, and it's wonderful, and I cannot understand why it is not enabled by default on every single cloud infrastructure out there, because of course you need it set on the guy sending you packets, not just you sending things. And anyway, if you can get it set, it's wonderful. And the clue that that's the problem is you log into a machine, you type PS, and then your SSH connection hangs. Because the output was more than 1,500 bytes.
Huh.
and you had some constriction, and it's a very good example. You're like, what? I'm trying to figure out why this machine is broken, and really it's broken, and it turns out that's the problem. And
thank you. I have not encountered that in the field, and that sounds like an important safety tip.
It happens to me, for me, regularly, because I have an V6 over V4 tunnel, so that I always have V6,
right.
And I experience this problem, and I just wish, trying to convince Google and Amazon and whatever to set the bit on by default in all their reference images and Ubuntu, and they're all like, well, do you have some data from the field to prove that it isn't going to break the internet? I'm like, oh, I don't have any data.
Gee, that sounds like another research avenue.
Well, no, Google has the data.
Oh, they have
Amazon has the data. They just need to go and look at their own data. Yeah, yeah.
So the point I was going to make about extension headers is that if you're doing any layer 4 inspection at a firewall, your extension headers, you can get sort of lost in there. There was an RFC, I should have included it, a couple of years ago describing how often extension headers, packets with extension headers were dropped on the internet. Things have improved significantly, but it's not perfect yet. But within your own network, where you have control over how you process things, generally things will work well. Ipv6, we sort of, we described them in detail. There's an RFC saying, here's what you should configure for Ipv6 in your firewall. Hey, I mentioned that before. So 13 out of 50 of the top Indian sites have Ipv6 MX records. Congratulations. That's mostly Google hosting your email. And that's why it works. 20 of, and there's a whole bunch more that, I guess, in addition to that use that. More Indian websites have Ipv6 for mail than for web. Come on. So spam is an issue because marking, so in V4, when you're doing large-scale spam management, you're generally doing some kind of IP reputation stuff. IP reputation is hard when you try and block one address or give one address a bad reputation, but you've got a /64 and you keep getting privacy addresses and getting new addresses. Some security tools. I want to kind of move through a bunch of things as quickly as I can. So I'm going to talk about the cloud. Talking about the cloud is tough because things change. They keep adding new capabilities. Everything I'm going to say is accurate as of sometime earlier this month. Things tend to get better rather than worse. The cool thing about cloud providers is a lot of your security concerns are actually managed by the cloud provider. So all of your neighbor discovery and router advertisements, all of that stuff, you don't worry about rogue device attachments in a virtual private cloud because it's a virtual private cloud. There aren't bad guys in the cloud provider's data center connecting rogue virtual machines to your virtual cloud. That's just, it's impossible, and they have controls over it. That helps a lot. They're doing IDS protection, so they'll block host scans. All of the, a lot of the concerns that we have over IPv6 related security things that I mentioned are just managed by the cloud provider. That's great. They also do a great job of providing you documentation. If you're subject to any kind of regulation that you need to provide an auditor information about your security, they do a lot of that provide a lot of that documentation for you. Also very handy. Now, it doesn't help with your VPN misconfiguration. That's still your problem because that's a client issue. It doesn't help with spam filtering because they're not usually hosting your mail, but then again, mail hosting does actually help with that. And processing extension headers, again, doesn't necessarily really apply inside a cloud. They're not really good at that custom stuff in terms of custom packet headers. But most of the rest of it is just managed. If you have a cloud provider that supports V6. So, and the cloud provider is actually motivated to support V6. There are, in the IPv4 address market, the biggest providers the biggest buyers of address space have been the major cloud providers. And there's huge outstanding demand for large blocks of IPv4 address space. If you are sitting on a /8 that you're willing to sell, please let me know. I'd be happy to help you find a buyer, and I'll just charge a small commission. So, okay, major cloud providers include Microsoft Azure. You can get an IPv6 address on a virtual machine. You can get an IPv6 on the outside of a load balancer, but you can't get IPv6 on anything else in Azure, as far as I can tell. It's pretty grim. Even within those two products, the virtual machine and the load balancer, several specific limitations that you have. You can't you can't configure IPv6 over their web portal. You have to use the CLI or one of the API systems. The IPv6 behind the load balancer isn't globally routable IPv6. It's not globally unique IPv6. It's ULA, which means you can't just, if you assign v6 to a virtual machine behind the load balancer, you can't SSH to that v6 address because it's load balanced and it's a private address. Private in v6. This is back to the NAT question. Why are we doing this? There's no reverse DNS, which, do you really care? The VMs, even if they are dual stack, will still use v4 only. In some scenarios, that's a problem. Here's the biggest one that really, this is why I put this in red. Microsoft says in their documentation that you can configure their network security, what they call them, network security groups for your dual stack virtual machines, meaning you can apply security policies to a dual stack virtual machine, but it only applies to the IPv4 instance. It doesn't apply to the IPv6 address. That's a major problem. You think? Gee, you get no security on IPv6? That sounds like a major problem to me. You can only do certain load balancer configurations, and you can't change them once they're done. And the health probe. So most important thing when you're deploying IPv6, this is deployment guidance, most important thing is to monitor v4 and v6 independently, so that if v6 goes down, you notice that it's down. If you're only monitoring a server by name, it'll come up whether it's v4 or v6. As long as one of them's up, it'll still work. You need to know if your routing fails. Microsoft will monitor only the v4. And if v4 goes down, it will take down both v4 and v6. So here's a little diagram to show how bad this is. Your security only applies to IPv4 and not to IPv6. So that seems, okay, you sort of inferred my opinion on that. Google says all VPC networks use the IPv4 protocol. Great, thanks guys. You can get v6 on a load balancer, but only the outside of the load balancer. Anything inside is v4 only. The forwarding rules, generally forwarding rules they charge for, but once you have the v4 forwarding rules set up, they don't charge you more for v6 forwarding rules. But a reserved address, they do charge you for. I can't imagine why they charge you for a reserved v6 address. It's not like those are expensive. Oh, and I even listed the price for Mumbai. That's basically what you get with Google. Oracle, you can, for their Service Cloud, which is their tech support service, you can open a tech support ticket, and that's the only thing you can do with Oracle. So they've got no v6 as far as am concerned. The exception is all the cloud providers will at least respond to DNS queries over v6, and you can populate quad A's. Amazon is the great story. I used to give them a lot of grief about their terrible v6 support, but just over the past 2 years, they've been really regularly adding more and more v6 support, and it's really pretty good. Most of their services do support v6. Their management console doesn't, their firewall console doesn't, their identity management console doesn't. Basically, anytime you're doing a web connection to it, that doesn't support v6. Their documentation's not available over v6. But okay, they need to add some quad A's. But, and most of the devices still require an IPv4 address, but I've been able to block the IPv4 address using security groups for most things. So it gets assigned a v4 address, but it doesn't have to use it. I'm going to kind of rush through these things fairly quickly because I'm out of time. VPCs work well. It's automatic. When you create a VPC, you just say, you pick a CIDR block for v4. By default, it says no IPv6 CIDR block. You just check, give me a v6, and it gives you an Amazon v6/56. When you create a subnet, you go down and you say, choose your subnet within that /24 or whatever, /16, and then a v6, you can set a custom prefix there. Containerization, there's a long video, 45-minute video that's fantastic on containerization and IPv6 and why we can't have nice things. It's really fantastic video. I love that video. Their CloudFront service actually is dual stack by default. Fantastic. But it's from your source to their cloud is still v4 only. Akamai's the same way. I don't think that's the end of the world. It kind of bugs me. They have some features that are still a little strange on the cloud, but they're not. You can do it. It'll still work. RDS is good. Lambda is their sort of, you don't get a virtual machine, you just upload code and execute it. That doesn't support v6 yet. It's what?
It's serverless.
It's what?
Serverless.
Serverless, yes. That doesn't support v6 yet. Their simple notification service doesn't support v6. I haven't encountered a case where that was a problem for me. And their application load balancer is v4 inside. Again, I don't think that is terrible. They provide great security, and whew, sorry for rushing through those, but I think this is a great conversation. Thank you. I think this is a great conversation. I really appreciate that we had basically the entire middle hour of the conversation was a dialogue with things that you guys want to talk about. I really appreciate that. Thank you.
Yeah, sorry we took up so much of your time, Lee. There's great stuff. Yep. No, so thank you so much.